it's fun.
You should say this kind of thing in the end of the lecture, not in the beginning of the next one.
Why?
Because that will make sure people are coming.
Or not. Well, you know, the course as a whole. The course is a course as a whole, not a... Let's see if that works. Yeah. What happened? Are you with me? Can you see my...
Started screen sharing, but we see a blank screen.
I think there may be a... Wait, I think maybe the connection cable is not so good. So just a second. Again, one of those. Oh, I think now it should be okay. Can you see it now?
Yes.
Yes.
And hopefully we're not going to get a lot of these technicalities. So the plan for today is to complete the discussion about Feynman rules. So we're still under discussing the decays and scatterings. Decays and scatterings. And then I want to already start to go to the next subject, which is the photon, basically, the QED, quantum electrodynamics, and the description of a photon within the quantum electrodynamics. That requires a little bit more. Okay, we start to do somewhat more in-depth quantum field theory because we will merge some things from relativity that we discussed with some quantum mechanics that we did not discuss. So I assume that you do know some things about quantum mechanics. If not, then you will be responsible to tell me that. Okay? But first thing first. So last time we started to discuss Feynman rules. If I go even one step before that, I discussed the Fermi's golden rule. So I said that there is a golden rule for decay and a golden rule for scattering. In quantum mechanical textbooks, you'll find the derivation of the Fermi's golden rule for the non-relativistic systems. That's why I'm hesitating whether I should give it, because it's relevant, but only for the quantum mechanical systems. So just the bottom line for a decay said that gamma is S over 2m1 integral over m squared 2 pi 4 delta 4 p1 minus p2 minus p n multiplied by pi j equal to 2 from 2 to n of 1 over 2 square root of pj squared plus mj squared d cube bj over 2 pi cube. So this is the decay of particle 1 into particles 2 plus 3 plus n. As we said, is a statistical factor, and the rest are the momenta. Now, when we speak about the two-particle decay, this can be simplified. So particle 1 decays into 2 particles, 2 plus 3, then gamma is just S divided by 8 pi m1 p, and then m squared, where p is a certain value of the momentum, which is really just depends on the mass of 1 over 2 m1, and then square root of m1, the 4 plus m2, the 4 plus m3, the 4 minus 2 m1 squared m2 squared minus 2 m1 squared m3 squared minus 2 m2 squared m3 squared. And of course, the mean lifetime of the particle, tau, is 1 over gamma. So if we know what is the masses of the particles, right, the initial mass and the final masses, and we know what is this statistical factor S, which really depends on how many identical particles we have there. And what else do we need to know? Of course, the scattering matrix M. Then we know what is the decay lifetime. And then we had the golden rule for decay, for scattering. Which is derived in a very similar way. So for two-body scattering in the center of mass frame, so two-body scattering in the center of mass frame, we have that the sigma, the omega, right, the differential cross-section is 1 over 8 pi squared S m squared divided by E1 plus E2 squared, and then E final magnitude over P initial magnitude. Right. That's the result that we got. Now, I argue that the dimension of M really depends on the number of particles involved. Right? It's a dimension of momentum to the power of 4 minus M. Right? So in this two-body scattering, so dimension of M is M to the power of 4 minus N, and is the total number of particles involved. So M is dimensionless here, but if we have a single particle decay, the M does have a dimension of momentum. Okay, now the question that remains is to actually calculate M, this matrix element. And for that, we use Feynman rules. Now, Feynman rules are really model dependent. So for different models, we have different rules. But the basics are quite similar to all of them. And I'm teaching you now the Feynman rules for a model which is not a physical model. It's not a real life model, but it's a toy model. And the reason why is because we're treating particles as scalars rather than vector bosons and spin 1/2 fermions as particles really are. So Feynman rules. Right, these are model dependent. Right, they really, when you learn quantum field theory, you will get to Feynman rules, and you'll see that these are really derived from the Lagrangian. And it's a way of writing, after calculating quite nasty integrals, to be fully honest. Okay, that's what I can say about them right now. Okay, so here we have a simplified model. So our model is the simplest I can think of, that contains 3 particles. So 3 spinless particles contain 3 spin 0 particles, which we call them A, B, and C. A is the massive one, so it can decay into B and C. there are no antiparticles, so each particle is its own antiparticle. And there is only one way for them to interact. So there's only one vertex that is allowed, and this is the vertex that connects all three of them. There is only one interaction in the theory. There is only one interaction in theory that connects A, B, and C. So there is only one vertex, right? A particle, B particle, C particle. And A cannot interact with two B's. Again, this is a rule that, this is how I define my model, right? This is how I define this simple model. If we had a different world in which A can interact with two B's, it would be a different model. All right? Everybody's with me? So this is really the lowest order decay process, right? Or leading order. So the leading order. Right now, last week I showed you that one can think of other ways of the particle A to decay, but that would involve third order corrections, right? Higher order corrections. Right? Higher order corrections. Right, within this simplified model. So we have A, right? It can decay, has to decay into B and C, but then we can have another interaction, for example, like that B would turn into C and A would interact with the C to produce a B. Of course, this is here we have three vertices. The rules are the same rules. In each vertex connects A, B, and C. So we can have A that interact with the B and the C, and then they merge, produce back an A, and then it decays into a B and C. That's another three vertices, 1, 2, 3. So we have third order correction. So we can have A, B, C, and then the C, and then interact to get an A and B, and then they merge together back to a C. That's another correction. I realize that the only other one that I think we can have right now is this, right? A, C, B, turn into an A and C. And then they will merge together to a B. I think these are all the options we can have for three vertices. But you can see that once the number of vertices increases, right, we can have 5 vertices, the number of diagrams is going to be increasingly grow. But of course, the contribution of each diagram is going to be much smaller, so that is quite fortunate. Right? The theory also allows scattering. This is little third order correction. Not sure if it's 1 or 2 hours. We can have a scattering, right? Within this theory. So scattering, A plus A scatters into B and B, right? So the leading order how would I draw the leading order diagram? So what comes from the left?
Two A's.
Two A's, A and A. Since each particle is its own antiparticle, I don't need to have arrows. Then what gets out?
Two B's.
Two B's. What would be the intermediate particle?
Connect the dots. So there's a C going out and the C from each vertex.
It has to be C because that's the only option, right? Because each vertex connects A, B, and C, right? You all see that? From each vertex, there is A, B, and C. That's the only option that we have. What about scattering of A plus B? Goes to A plus B, so that's a scattering between an A particle and a B particle. Right, so you have an A particle and a B particle, right? They're coming. Now we can have two options, right? One is that immediately we get a B and an A, so T channel. So here we must have a C. Or we can have an S channel. You see here, and then we end up with an A and B. In all cases, we keep all the rules, right? Only three particles. Each vertex connects A, B, and C, and that's it. So everything is within what is allowed by the model that we define. So each of these diagrams, right, it connects the initial particles that enter the process, right, the final particles. So here we have initial particles, right? These are the initial. These are the final. And there are a lot of intermediate particles, right? So this would be the intermediate particles. So given such a diagram, how do we find the matrix M, the matrix element M? So for that, we have these Feynman rules. So Feynman rules tell us how to find the matrix element M from a given diagram. Now, the rules are actually quite simple. So let me write it down. So the first rule is simply the notation. So we label the form momentum of each of the incoming and outgoing particles by P's. Right, label the form momentum of each incoming and outgoing particles by P1, P2, Pn. We label each internal line by Q. Right. Q1, Q2, whatever. Don't skip these parts because otherwise they'll save you a lot of confusion. Then we keep an arrow beside the line. This is not the same arrow that we put on the line to represent the charge, but that represents the direction, the positive direction of momentum. Put an arrow besides line, besides each line. Besides each line, to keep track of the positive direction. Right? It's always forward in time for external particles, and it can have an arbitrary direction for internal particles, but it just have to be there. Right? So forward in time for external particles. Then arbitrary for internal particles. Okay, that's a simple rule. Rule number 2. Now we look at the vertices. And for each vertex, we write down a factor of minus ig. For each vertex, write down a factor of minus ig. G is the coupling constant. G is the coupling constant. That specifies the strength of the interaction. All right. Generally, G would include the charge of the particles, but here it's not, there are no charges, so we just ignore it and put it as 1. Okay. Rule number 3 is a propagator. That is, for each internal line, but just for the internal lines, we write down a factor, write it down for each internal line. We write a factor of I divided by Qj squared minus Mj squared. Now remember, Qj is the form momentum of the line, Mj is the mass of the internal particle. But in general, the particle is virtual, so Qj squared is different than Mj squared because it's a virtual particle, it's not a real particle. Right? It's off the mass shell. So we don't really have a trouble in writing it down. The next rule is conservation of the form momentum. So for each vertex, we write a delta function for each vertex. We write a delta function of the momenta, right? So 2 pi to the 4, that's notation, right? Say, delta 4 of the momenta. So let's write it as k, k1 plus k2 plus k3. Now, k represents the 4 momenta of the particles entering the vertex. Ki, 4 momenta of particles entering the vertex. Right? Which means that the arrows that we point at, that we draw in rule number 1 are pointing towards the vertex. What if the particles are outgoing away from the vertex?
And the arrows point away?
Yeah, the arrow point away, and what do we do with the delta function?
Minus the momentum.
Minus, right? We talk about conservation of momentum. The total momentum that gets in needs to be equal to the total momentum that goes out, right? So if a particle is outgoing, right? The arrow leads outward. Right? Then it's a minus sign. Then the 4 momentum is written with a minus sign. Of course, the delta function here is to ensure that we have conservation of energy and momentum at each vertex. Okay, at this stage, we wrote down factors of the propagators and for the vertices. Then we wrote down delta function. And then what we're left to do is to integrate over the internal momenta. So for each internal line, we write down a factor of D for Q, of course, with the right normalization. D for Qj divided by 2 pi to the 4. Again, it's a convention, the 2 pi's. Just easier to remember like that. And then, of course, we integrate over all internal momenta. Two more steps. When we do that, when we perform the integration, we will get some expression that would contain a delta function. So we have to cancel this delta function. Let's call it cancel the delta function. So the integration in step 5 leads to an expression that contains 2 pi to the 4 delta of the moment P1 plus P2 plus minus Pn. And this, of course, represents global conservation of momentum, momentum and energy, right? It's a four momentum. So what we do is we simply erase this factor. Erase this factor. And then multiply everything by I. This is a convention for the phases. We don't really have time to get into that. Multiply the result by I. And that's it. And what we get is M. And then the last, now the reason why we cancel this delta function, we will have to square the expression because we're really interested in M square, as you saw when we calculated the decay rate and the scattering rate. It's always with an M square, and we cannot square a delta function, but we don't really need to because we will get a delta function that we get out of the golden rule anyway. So it's to avoid getting us into a trouble of double integration. And then the last step is simply to repeat all steps for each diagram that we have, and then sum over all diagrams. And that's it. That's a prescription. Okay, let's see how we're going to actually use it. So example. Let's make several examples. So example number 1 is the lifetime of A. So we want to know, theoretically, what is the lifetime of the particle A, right? So we said that in our model, particle A can decay into particles B and C. So we're just going to look at the lowest order, leading order, contribution to the decay process. So lowest order contribution. Of course, I'm just going to do the simplest one. The harder ones are saved for later on. The really hard ones are saved for the exam. This is A, B, C, and D. Right? So we said that in rule number 1, we have to draw the momentum and we put the arrows. Right? So this will be P1, right? And it's incoming to the vertex. So P2, it's the arrow, it's outgoing away from the vertex. And this is P3. And it's going again away from the vertex. So I'm pretty much done with rule number 1. Now we have rule number 2. It says that we have one vertex. We write down a factor of minus IG. Now, in rule number 3, we spoke about, I think, internal lines. We don't have any internal lines, so I can skip that one. Rule number 4 gives us conservation of the form momentum. So for rule number 4, right, conservation of momentum. That gives us the 2 pi 4 times delta 4. Now remember the directions, right? So the incoming is only P1. We have 2 outgoing, so we have minus P2, minus P3. Again, rule number 5 speaks about internal momenta. We don't have any internal momenta. So rule number 6 tells us that we need to cancel the delta function and replace it by I. So far we just had a minus IG times 2 pi 4 delta 4 P1 minus P2 minus P3, right? But rule number 6, cancellation delta function, says that I can take all these parts, erase it and replace it by I. So we get minus I times I, this is just G, which means that M is equal to G. And that's it. So now that we know that M is equal to the coupling constant, I can plug it in the result that we derived it last week for gamma. So that means that gamma A is just G squared P divided by 8 pi MA squared. P is the magnitude of the outgoing momenta of either particle, and that's given by the long equation that we presented previously. All right, it's A, B, and C. Really simple, isn't it? Of course, we have the tau, the lifetime is one of them. That's all. As simple as that. Let's take a second example. So the second example, questions about that? Any questions, anybody? Well, there are some students, I don't see your screens, so I can't even see your faces. I don't even know if you're here. Any questions? Let's take another example. Let's take a scattering example, right? So example number 2. It's A plus A goes to B plus B, right? This is a scattering. Annihilation, anything. So again, if we look at the center of mass, right? What do we have? We have center of mass frame. We have P1, P2, right, of A and A. So that's before. And the after part, right? Then we have that, you know, P3 and P4. PB. Right? I have some angle here. Theta. Right? That's what happens in the center of mass frame. So the lowest order contribution you already plotted it. Well, this comes from the T-channel diagram that we had previously. So we had an A, B, B, C. That is the T-channel. Okay, so again, let's follow the rules. So rule number one is to draw the momenta. So let's say we have here a momenta, P1, P going in this direction. And here we have a P2 going inward in time, right? And then we can have P3 going outward, P4 going outward. Now I said that the internal lines, it's custom to call their momenta with a Q's. So we only have one, so let's call this a Q. Let's say it goes in this direction. And I said the direction for the internal ones, we don't really care, just a matter of convention. So rule number one, just draw. Rule number two, we have how many vertices? Two, right? So the contribution should be how much?
Minus d squared.
Right, each vertex contribute minus ig, so we have a minus ig squared. We also have one internal line, right? So for the propagator, we have internal line. And the internal line would give us a factor of I divided by Q squared minus MC squared from the internal line. And now we said rule number four is that we have conservation of the form momentum at each vertex. So we have two vertices. So we have two delta functions. So we have 2 pi to the 4 times. Now the direction of Q, it's important that we don't confuse, right? So if you look at the lower vertex first, we have P1 minus P3 minus Q. And if we look at the upper vertex, what do we get? What do we get to the upper vertex?
P2 plus Q minus.
Come incoming arrows to the vertex, right? Right. So to this vertex, we have 2 incoming arrows, P2 and Q, and 1 outgoing, which is P4. So we have 2 pi to the 4 delta to the 4 P2 plus Q minus P4. And we have only 1 internal momenta, right, Q, so we have 1 integration. So rule number 5 say that we should have D4Q divided by 2 pi to the 4. So if we take all these together, and we combine all these together, well, then we get a minus I, minus from here, I from here. 2 pi and 2 pi to the 4, they cancel, so we left with 2 pi to the 4. Then we have G squared. Right, then we get the integration over D4Q of 1 over Q squared minus MC squared times delta to the 4 P1 minus P3 minus Q times delta to the 4 of P2 plus Q minus P4. Then the integration is over D4Q. Now we really have a delta function here. Well, we have 2 delta functions. So we don't really have to carry the integration because the delta function will just cancel with the integration. Right, so you can simply use, rather than the integration, we just write down Q, right, is just P4 minus P2. And we get minus I G squared. And 1 over Q is P4 minus P2 squared minus MC squared. And then delta 4 of P1 plus P2 minus P3 minus P4 times 2 pi to the 4. Right? So as I promised you, by the end of rule number 5, we are left with no integration, but 1 delta function, right? And this delta function, as stated, represents conservation of energy and momentum. So what is left is rule number 6. And rule number 6 says we cancel the delta function, right? Erase it and multiply it by I. Right? So we take this 2 pi delta function, erase it and multiply it by I instead. And we get that M is just G squared divided by P4 minus P2 squared minus MC squared. Which, by the way, I think I was asked about that last time. Why do we call the T-channel T-channel, right? Because the Mandelstam T variable appears right here. So when we carry the integration, then we end up with a Mandelstam T variable. right? This P2 minus P4. That explains it. Okay, did we finish? Did we finish?
You need to check all the other orders.
Did what?
To do the same thing for the rest of the orders. The rest of the...
Yeah, but what about the leading order? Did we finish with the leading order?
Isn't this just a T channel?
This is T channel, yeah. Okay. It's drawn here.
S channel?
We have to write gamma. We didn't write gamma.
What do you mean gamma? I don't have a gamma. This is scattering.
We have to use the Fermi rule to finish.
Yeah, it's not gamma. It's sigma.
Yeah, sorry.
Yeah.
Sigma.
No, well,
Sigma.
even before that.
The S channel?
No, I don't have an S channel here.
There is how we called it, the other one, not T, not S. The
U channel.
U channel.
Right. The B particles are identical. Right. So if the B particles are identical, right, then we also have the U channel. A, C, B, B. Right. But again, we have a P1, P3, P2, P4, Q, right? By the way, why can't I have an S channel here? Remember, right? This is an S channel, right? Why cannot I have?
Because A and A can't annihilate.
Exactly, right? Because I said that in each vertex connects only A, B, and C within the framework of this model, right? I specified the model by arguing that in this specific model, each vertex has to connect A, B, and C exactly. So I don't have the option of having two A's in this model. I can have maybe a different model, but in this model, I don't have this. Okay, so what about this channel, U channel, right? So it's the same order, right? It also would be of the order of G squared, right? And the only difference is that I just twisted the B lines, right? Because I said B particles are indistinguishable, right? Are the same particles, right? But of course, I don't really have to work very hard, right? Because what's the difference between this diagram and the diagram, the T diagram that we had previously?
Only the momentum.
Exactly, it's only a change in momentum. It's only just P3 we change with P4, that's all. Right. So I don't need to do any more calculation. right? So I can use so we use the same calculation. Right, and simply replace and write down to leading order. With M, just G squared divided by P4 minus P2 squared minus MC squared plus G squared divided by P3 minus P2 squared minus MC squared. This is a Lorentz invariant. This is scalar quantity, and that's always the case. Right? M is a scalar quantity. Lorentz invariant, which is another way of saying that two observers, different frames, would get the same result. So we did do the calculation in the center of mass frame because that's easier for us, but any other observer would calculate the same. So just to show you that this really is what we think it is, right? So let's assume for simplicity. So let us assume that MA is equal to MB is equal to M. So we have a scattering between two particles of the same masses. They're different. They're still different particles. They simply happen to have the same masses. In that case, what will be the mass of the C particle? Well, if MA is to be able to decay to B and C, that means that MC must be equal to 0. So in that case, we have that P4 minus P2 squared minus MC squared, right, is just P4 squared plus P2 squared minus 2 P2 dot P4, which is just minus 2P squared times 1 minus cosine theta. Right, I'll refer you back to the scattering process that we had. We have it here. And then P3 minus P2 squared minus MC squared is, of course, P3 squared plus P2 squared minus 2P2 dot P3, which is just minus 2P squared 1 plus cosine theta. P is the magnitude of the incident momentum of particle 1 or 2. Center of mass frame. So if you plug it in the result of M, then we end up that M is simply minus G squared over P squared sine squared theta. And using that result in the calculation we had for the scattering cross-section. So going back to the derivation we did previously, we end up that this sigma over the omega, right, the differential cross-section, is 1/2 of g squared divided by 16 pi e squared sine squared theta squared. Now the 1/2 comes from this statistical factor s, right? S is equal to 1/2 because we have two identical outgoing particles. So interestingly, you know, this is the same as you get in the Rutherford scattering. The cross-section diverges when you go to small angles. And the total cross-section is infinite. Okay, but the important thing to remember, so I gave you this prescription, really, is that these Feynman rules are specific for this simplified model that contains only scalar particles. Okay, let me stress that. The Feynman rules written here are specific for the simplified model of scalar particles. Now, fact is that this is not really a big drawback because the Feynman rules for real life models that contain fermions, spin 1/2 fermions and vector bosons are not that different than what we had here. There is a slightly more complexity because of the existence of the spin. So there is some extra term there, but not something that that is conceptually different. So once you get used to that, then it's quite straightforward to generalize that to other models. Okay, I'm not even sure if we'll go into the exact Feynman rules for real life models, because if you understand the concept, then getting to exact technical details, that requires to go into somewhat deeper into why this is so, and for that we need to go deeper into quantum field theory than we have time to go to, I'm afraid. Questions about that? Any questions? No? If not, okay, then I finished what I have to tell you about decays and scattering, at least for that level. I haven't brought the Fermi's golden rule for now. I'll see. Okay, I may do it one time, but I'm not going to do it right now. So right now I'm going to go straight away in the remaining, I don't know, 25, 30 minutes that we have to go to the next subject, which is discussion of the Maxwell's equation, quantum electrodynamical description of the photon, And that will lead us, then we'll generalize that to Klein-Gordon equation. And after that, we'll describe Dirac's equation. But first thing first. But before I'm going to get into that, I should ask you two questions. Question number one, do you want the 5 minutes break or not? No? You prefer that we
Go straight.
go straight. Question number two, I'm asking again, do you have any questions? If not, that means that everything is clear. I mean, I'm the first one to admit, I mean, I gave you the Feynman rules are very simple. The derivation is not that simple, but the rules themselves are quite simple. And I did not give you the full derivation, again, because I keep on saying that because I don't like the fact that I'm not giving you the full math, but otherwise it would just be too much of a mass and I would lose you, which would be a pity. That would come in a more advanced course in particle physics, but this will be for a master's level. Okay, so the next subject is Maxwell's equation and the photon. Since the photon, let's start with that. Okay, that again brings us to describe a little bit about the concept of quantum field theory. Specifically, what we're doing now is called quantum electrodynamic, which is the quantum field theory of electromagnetism. And that means that this is a way of merging classical electromagnetism with quantum mechanics. And in this theory, as we're going to see, well, as I already told you, the photon becomes pretty important. Now, when you think of it, what you learn in classical electrodynamics, right, is that the force between charges, how do charges interact with each other, right? Classically, what happens? What happens classically when you learn that in your E&M course? It's a real question.
A charged particle creates electrical magnetic fields which affect other particles.
Right. So in classical physics, right, 19th century physicists, they will tell you, yes, this is what happened, right? The force between charges originates from electric and magnetic fields, right? What happens in quantum physics? So when we go to quantum physics, right, the fields are being quantized, right? And when they quantize, they get the properties of a particle. This particle, as we're going to see, is really a photon, right? So that means that if you agree with that statement, right, and you think of these two merged together, then you conclude that the photon essentially participates in all the interaction between all charged particles, all electromagnetic interactions between charged particles. Okay, now the way we describe the interactions is by exchange of photons between the particles. Now, when we speak of classical system, what happens in a classical system? Right, it's exactly analog to what happens in the Young's double slit experiment, essentially. Right, in the sense that there are the two charges, but classically they exchange very many photons, and they're all having low energies. And as a result, we don't see the discrete nature of the photons, and we treat it as a classical field, right? The wave nature of particles, if you want. But as opposed to that, we do have some experiments which show quantum mechanical effects, right? So we can think of the photoelectric effect as a classical example. right? Or a collision, high energy collision between photons and particles, right? So in such quantum mechanical interactions, we're in the opposite limit, where we have interaction that involves very few photons on the one hand, right? So very few photons are exchanged, but it can be only a single photon, right, in certain cases. And so we can actually see the quantum mechanical nature of this interaction. Okay, so let me just briefly summarize what I just said. So classical E&M, force between charges originates from electric and magnetic fields. Right? In quantum physics, field is quantized. That's the properties of particles. Right, which is the photon. So we're going to say that it contains all the characteristics of a photon, this particle. And when we merge these 2 points together, we deduce that the photon participates in the interactions. The photon participates in electromagnetic interactions between charged particles. Right, so each interaction is really described by photon exchange. EM interaction is described by a photon exchange, or photons, a photon by photons exchange. Between the particles. So let's see how this works in reality. Questions? No? I'm a little bit concerned that you don't have questions. Okay, so quantum mechanical description of a photon. Okay, so before I'm going to do that, but before I'm going to do that, I need to introduce to you something which I'm not sure that you've ever seen. And this is the covariant form of Maxwell's equations. Just out of curiosity, how many of you have seen the covariant form of Maxwell's equations? 1, 2, 2. That's it? Okay, so I do have to introduce it. As we're going to see, the covariant form will lead us to introduce the vector potentials. You know the vector potential, it's the same potential that you've seen. But you're going to see that when it comes to the quantum aspects, it becomes much more important than classically. I mean, classically, I remember I didn't fully understand why you need it at all, except for, mathematical game. But when it comes to quantum mechanics, then you're going to say that it actually is the most important entity. So there is a reason why you were taught that. But first thing first. So the first thing we need to introduce is units. And the problem is that in electromagnetism, there are very many different units which are in use. So let's just go over that briefly. Units. So in E&M, there are many units. Unit systems in use. This corresponds, for example, to what is the unit of the electron charge, right? So the unit of electron charge right, is described by the electric field, right? So electron charge produces an electric field, stationary point charge, the electric field of a stationary point charge is E, right, is K times Q over R squared, the radial direction. Right? And the question is, what is K? So in SI units, which is the MKS, right? K is 1 over 4 pi epsilon 0. Right? In CGS units, it's also known as Gaussian units. What is K? No, it's hard.
One.
The 1, yeah, exactly. K is just 1. But the units that we love for some reason is the Heaviside Lorentz unit. So in Heaviside Lorentz units, then we have epsilon 0 is 1, like the vacuum permittivity. And since we have 1 over square root of epsilon 0 mu 0 is C, and since C is 1, and C is equal to 1, then we end up with mu or 0 is also 1. So there is differences in charge, right? So the unit of charge is different in the different systems because eventually it follows measurement of the Coulomb force, right? Because the force is something that we can measure. So let's write it down, right? So the relations relation between the unit of charge in the different systems. This follows from the measurement of the Coulomb force. So the charge in the Heaviside Lorentz unit is just square root of 4 pi. Yeah, I'm okay. Sorry. Heaviside Lorentz units, K is 1 over 4 pi. Okay, epsilon 0 is equal to 1, usually to 1, but I didn't write down the K eventually. It's just 1 over 4 pi. So the Q Heaviside Lorentz is square root of 4 pi of Q in the Gaussian unit, and that's 1 over square root of epsilon 0 Q in the SI unit. And similarly for the electric field, in Heaviside Lorentz units is 1 over square root of 4 pi the electric field in the Gaussian units, then it's square root of epsilon 0 the electric field in the SI units. The cool thing about that is that the fine structure constant, which is unitless, is the same. Okay? So the fine structure constant is independent, always gets the same value. Like in all systems. Alpha is just U, say, Gaussian unit square divided by H over C. Just U squared Heaviside Lorentz divided by 4 pi H over C. Just U squared SI divided by 4 pi epsilon 0 H over C. And it's always number 137. Now, I do have to tell you, I'm going to use Heaviside Lorentz because this is what you find in most textbooks, but not all of them, which was kind of annoying when I prepared this lecture, because Griffiths, which I'm semi-following, is using Gaussian units, but other textbooks use Heaviside Lorentz units. So I very much hope that I'm not going to introduce any strange factors of 4 pi that are floating somewhere in the air. Okay? So here, again, the reason is because many particle physics textbooks use that. This is kind of the standard. Okay? So let's go now to write down the covariant form of Maxwell's equations. Well, let's start. Not finish now, we'll finish on the first one. So covariant, questions about that, by the way? Any questions? No? No? So you write down the Maxwell's equation in Heaviside Lorentz units, right? So H units. We have the Maxwell's equation. Right. You want to write it down for me? What's the first one?
I can do that, but only in SI.
Only SI.
Take it or leave it.
I see. Gauss law. Right. Right. Faraday's law. X is equal to 1, then you have right? Faraday's law of induction. And then no magnetic monopole. Is everything okay? Can you see me?
I think you disconnected and then reconnected,
Yeah.
so your iPad display just vanished.
The whole universe really just disconnected, but it came back.
Okay. Wait, is it recording? Oh, no, it's recording.
It is recording, but we can't see your iPad.
Yeah, I can see that. I'm going to share it again. I'm totally not sure what happened. Okay. Sorry for these technicalities. Apparently, when I'm from the office or from home, it doesn't really matter in terms of whether it's okay or not. So where were we? Yeah, ampere. So nabla cross B minus 1 over C dTE is J, right? J over C, but C is equal to 1. So nabla cross B minus dTE is J. Right, this is amperes now. Ampere. Okay, so this is Maxwell. 1, 2, 3, 4. And here is just a natural unit where C is equal to 1. You know that. Okay. Now I want to write these equations in a much more compact form, which is it's the same equations, but a compact form which will also manifest the fact that you know, there is a strong connection between electromagnetism and special relativity. Right? You've heard about that, I guess. Yeah? No, or maybe. Yes, no, maybe? You refuse to answer. How many of you have heard about the connection between electromagnetism and special relativity?
The inspiration.
The sense that Lorentz transformation were first derived in order to work with electromagnetism?
No, in the sense, well, this I don't know actually, to be honest. I don't know if Lorentz transformation was derived first for that. In the fact that, you know, electromagnetism is consistent with special relativity. You know, Galilean transformation, for example, which is in the heart of Newtonian mechanics, is inconsistent with special relativity. But E&M does, and you can see that right away from, you know, the wave solutions to Maxwell's equation, which the waves in vacuum travel at the speed of light. Okay, now in order to do it properly, I need to do some more thing about special relativity, which I did not do really, because I didn't think that I'm going to need, but now I think I actually did need. And that is to have a slightly better definition of what is a vector. Right? When we discuss special relativity, we have, I have introduced several vectors, right? We spoke about the position vector, about the velocity vector, about the energy momentum vector, right? So we had several vectors which we introduced, but I did not really make a clear definition of what exactly is a vector. This is a part that is being done in the course of general relativity, but apparently it will be good. It turns out to be quite useful to have it here as well. So, so the correct mathematical definition of a 4 vector goes as follows. The mathematical definition of a 4 vector. Right. So a contravariant 4 vectors. This is the, remember we spoke about contravariant and covariant. So the contravariant, this is regular vectors, right? Is an abstract object, right? It's an abstract object whose components transform the same way as the coordinates under Lorentz transformation. Okay? Let me say it again. A contravariant for vector is an abstract object or any abstract object, any abstract object whose components transform. We have the type here. As V alpha goes to V alpha prime, which is lambda alpha prime beta, V beta, when the coordinate system transforms in the same way. This is the precise definition of 4 vector. So when we make a transformation from one coordinate system to the other, so 2 different observers, right, which sit in 2 different inertial frames, right, the coordinates of the vector as described by each observer change. But the vector itself, being an abstract entity, nothing happens to the vector. It's something which takes a little bit time to digest, what I will say. The vector is abstract. The way we describe it change between the observer. Okay? Now, the change in the description, it happens in such a way that the vector itself, which is an abstract entity, doesn't care about the change in coordinates. Nothing happens to the vector. Right? So in that sense, we can think of a vector as a linear map between the 4 coordinates. And again, I'm not going to get into the details, but the coordinates would themselves form a covariant vector, dual vector, and R. So I write it down. It's a little bit abstract, but that's the exact mathematical definition. So we can think of a vector as a linear map between the 4 coordinates and R. The advantage of this way of thinking, which is extremely abstract, is that we can generalize that to the concept of tensors. So a 2-0 tensor can be thought of as a linear mapping between 2 covariant vectors and R. Right? And a 0-2, so to write it down. So a 2-0 tensor is a linear map between 2 covariant vectors and R. And the 0-2 tensor is a linear map between 2 contravariant vectors in R. Now the fact is that we have already seen 1-0-2 tensor. I just didn't call it like that. That was, of course, the metric tensor, right? So for example, the metric tensor, right, G mu nu, right? I treat it as a linear map between two tensors and two vectors and R, right? What is this linear mapping? This is the inner product, right? So if I have G mu nu, A mu, B mu, B mu is just A mu, B mu, which is just a number, it's a scalar. Now, again, I'm not really getting into that. To get into that, you have to go to the course in in general relativity. Then we do go deep into that. But the way of thinking of a vector as a linear mapping is something which very much helps us generalizing this concept. And it's also very important in the sense that, you know, thinking of a vector as an abstract entity which does not care about the observer. And the only thing that changes when two observers look at it from different directions is the component of the vector, right? There is something which is very fundamental in this description, because the whole idea behind, you know, this description of physics is that the physical system itself doesn't really care about us, the observers, right? We're just looking at it, and the coordinate is something that we define to help us describe the system. But each one of us can define different coordinates based on whatever is more convenient to us. And the physical system doesn't care about it. Having said all that, I'm going to introduce you to combine the electric and the magnetic fields into one 2-0 tensor. And that is known as the electromagnetic tensor. Other names that you might have heard of is the field strength tensor or the Faraday tensor. But how many of you have seen the Faraday tensor? It's something which normally you encounter in advanced E&M, though I'm not sure that they describe it, what exactly the exact definition of a tensor is. But it is. So we can combine the electric and magnetic fields into a 2-0 tensor known as Faraday tensor. Or electromagnetic tensor. Sometimes it's also called field tensor. It has very, very different names. And because it's a 2-0 tensor, I write it with two upper indices, F mu nu. And it goes the following. Now the definition, again, it's convention. And for a reason which, again, I told you makes it, tries to confuse me. The convention in particle physics is opposite in sign to the convention that is used in astrophysics. And it goes like that. So it's a 0, and then have a minus E1, minus E2, minus E3. It's antisymmetric, so it's a E1, E2, E3. There are zeros on the diagonal. And then there is a minus B3, E2, and minus B1. And it's inverse, so it's V3 minus V2, V1. Of course, EX, E1 is EX, E2 is EY, E3 is EZ component. And the same for magnetic fields. Now, again, this is what you'd find in particle physics textbooks, and this is exactly the opposite in sign. So, F mu nu in astrophysics textbooks would be with a minus sign to what is written here. Why? Because we want people in particle physics not to be able to discuss properly science with people in mass mechanics. Okay, I ran over time, but I introduced you this electromagnetic tensor, and I will show you how to use it. It's just a compact form of putting all the fields together in a matrix form. And I'm going to show you how I'm going to write down Maxwell's equations using this Faraday tensor. And this will be on Thursday. Do you have any questions? Anything? Anyone? If not, then I thank you very much for your time. And we'll proceed with that, and then we'll go on. So the plan for Thursday, I'm not sure how much we'll do, because I want to do a tutorial as well, because we started to say a lot of new and more technical things now. And we'll proceed with that because we're going to quantize that fields on Thursday. Well, not sure if how much we'll have time to do on Thursday and how much we'll do on Tuesday, but that's basically the direction we're going to do. We're going to write them down in a compact form, and then we're going to start quantizing them and see what we get. I can tell you what the answer is going to be like. We're going to get the photon, and we're going to get the photon to see all the properties of the photon that we're going to get out. All right. So thank you very much, and I'll see you on Thursday.
Thank you.
Do the stop sharing and the stop recording.
Thank you.